Good afternoon, everyone. Thank you all for coming. My name is Fangjin, and my colleague here is Nelson. So both Nelson and I are software engineers at a fast-growing San Francisco startup called Metamarkets. So today we wanted to talk to you guys about this idea of how you can trade off accuracy in your data and accuracy in your query results in order to gain improved performance in your systems and vastly reduced data storage for your data. So this talk is really based off of our own experiences and some of the problems that we faced and some of the trade-offs we've had to make in order to solve those problems. So today we'll go over the problems of managing a large amount of data. We'll go over the data itself, what it looks like, and we're going to talk about some ideas of how you can throw out some information about this data in order to make it a little bit easier to manage and a little bit easier to store. Finally, we have basically two case studies where we're going to discuss two approximate algorithms that we've actually worked with ourselves and like the problems that they're meant to solve. So as I mentioned, Nelson and I work for Metamarkets. And Metamarkets is a data analytics company that's primarily focused in the advertising technology space. So most of our data and most of our customers comes from this process known as real-time bidding. Now, if you're not familiar with real-time bidding, it's fairly simple from a high level. Basically, let's say you're the cool guy there with the sunglasses. Every time you load a web page, there's actually a background process that occurs where many advertisers will try to programmatically outbid each other such that they can display an ad to you when your web page loads. So real-time bidding, there's a lot of components and there's a lot of players in this space. And because the process is programmatic, there's a lot of data that gets generated. And sort of the value add of Metamarkets is being able to make sense out of all this data. Now, from an engineering perspective, many of the problems that we solve on a day-to-day basis are around improving the performance of our systems and trying to reduce the cost of storing a lot of data. So when you're dealing with like billions of events, it can be expensive to store this data and it can be expensive to process this data. What we've had luck doing is we try to reduce the amount of data that we have to store. So we try and discard information that we don't think is critical. And by reducing the amount of data that you have to store, you oftentimes get greatly improved performance in your systems. Now, reducing storage, as I mentioned, fundamentally means sometimes throwing away information. And throwing away information can lead to a reduction of accuracy of your query results and of your data. So the type of data that we typically deal with is event stream data. So our data always has a concept of a timestamp. Now, in this very simple example, we have two columns. We have a timestamp column, and we have like a bid price. So this data is basically saying how much money was made at a certain point in time. Now, for one of our customers, they may potentially see millions, if not billions, of these events in a span of an hour. And for a lot of our customers, they don't particularly care about a single event. Like, they don't really care that like 3 cents was made at this exact millisecond in time. What they care about a lot more is aggregates. How much money was made over a minute of time, or how much money was made over an hour of time. So because a lot of our customers care more about a summarized view of the data, this means we don't really have to incur the cost of storing all the raw events. So what we actually do is we store a summarized representation of this data. And in this example here, basically we're storing an hourly representation of the amount of money we made. So we truncate the timestamps and we aggregate all the bid prices, and we store basically a single row that represents all the raw data in the span of an hour. Similarly, we can also store a daily representation of the data. So basically what you do here is you summarize or you aggregate all the different revenue numbers for the hours of the data, and you get this final daily view. So this is a plot of the savings that you get using summarized data. Basically, you can see that you're storing a lot less information by summarizing your data versus storing the raw data. And similarly, you see a vast reduction in computation cost with summarizing data versus scanning and using raw data. And you should familiarize yourself with these graphs because this idea is going to come up again in future slides. Okay, so data summarization, fundamentally what we're doing is we're throwing away information about individual events. And what we gain in return by throwing this information away is drastically reduced storage and vastly improved query performance. On average, in our systems with our customer data, we see that by storing summarized views of our data, the data volume is about 40 times less than had we stored the raw data. And the trade-off, once again, is we've lost some information about individual prices. There is some information that's being lost. And it turns out to solve different classes of problems, this information that we're losing is actually kind of important. And for certain types of problems, it's not immediately obvious about how you can do data summarization. Okay. So I have sort of the first of two case studies where we're going to go through an example that we actually faced as part of our jobs. And the problem is around finding the unique number of elements that exist in a set. The application for this, the problem came from our customers, and the application was really measuring the unique number of users that may have seen a particular ad. So there are basically two ways that we can go about solving this problem. One of the ways is to trade off some accuracy information, and in return we gain some performance and storage benefits. The other way, the more direct and exact way, is the way I'm going to talk about first. And that way is to basically not throw away any information. We don't make this accuracy trade-off. Instead, what we do with the exact solution is we store every single username that we see as part of our data set. So in this example data here, basically, once again, we have a timestamp column. And then for each period in time, for each moment in time, we basically have a username associated. If we want to summarize this data, what we would do is we could have an hourly entry. This represents the users that we've collected over the span of an hour. And we store a set that contains all the unique usernames we've seen for that hour. Oops. Similarly, if we wanted to know all the unique users we've seen over the span of a day, basically what we do is we look at our hourly data and we take a union of all these sets here. And this final union set, the count of it would represent the unique users we've seen over the span of a day. So the exact solution, the storage and computation costs are linear in the number of unique users that you've seen. And we're not throwing away any information. We're keeping all the usernames that we've seen. So the accuracy of our data, much like Legolas here, is 100%. The problem that we see with this data, the problem that we see with this approach is basically when you have very high cardinality dimensions, it becomes somewhat infeasible to store every single value in that dimension. So for example, if you want to store 10 to the 9 unique elements, this might require upwards of 48 gigs of storage. And that's a tremendous amount of storage for a single dimension of data. And most companies don't want to spend the bling to be able to deal with this much data for a single dimension. So when we were faced with this problem initially, we had a conversation with our customers. And what we found from that conversation is a lot of our customers didn't really care about the exactness of the results. And they were pretty comfortable with a few percentage points of error. So this kind of led us down this track of looking at a field called cardinality estimation. And there are there's much literature out there about how cardinality estimation works. For us, we kind of picked the technique that we thought was the best in the space, and that technique is known as HYPERLOGLOG. So HYPERLOGLOG nowadays, I would say, is fast becoming sort of the standard for cardinality estimations, and for very good reason. To store cardinalities of 10 to the 9 and above, basically you only required 1.5 kilobytes of storage. That is a reduction of 99 point, a whole bunch of 7 decrease in storage size. Like, that is tremendous, and for us it was like game changing. The computation time for cardinality in the trillions is constant, and the accuracy of our results was about 97%, which for our customers was like good enough. So the idea behind HYPERLOGLOG is, instead of storing all your data, instead what you store is a sketch of that data that represents some result that we care about. So what do I mean by that? Let's say, okay, so I'm going to have an analogy. And let's say we're trying to determine how many times we flipped a coin. Okay? So you know, with the coin flip, there's 50% chance of heads and a 50% chance of tails. One way we could determine this result is basically we store the result of every single coin flip as it happens. So we store the sequence of like heads, 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 tails, 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 whatever. One other way that we could arrive at the same result is basically, let's just maintain a count of the number of times that heads appeared. And at the end of the day, when we want to know how many times the coin was flipped, we can use the magical properties of probability and basically just double our count and arrive at our answer. Now, HYPERLOGLOG works in a similar fashion. The full details of the algorithm are a little bit complex, and for anyone that's interested, we'd be happy to discuss out the full details as part of our office hours. For now, I'm going to sort of talk about the high-level idea. So in HYPERLOGLOG, and going back to our coin analogy, in the coin analogy, we were storing a count. In HYPERLOGLOG, what we store is a series of buckets, and each bucket is maintaining some value within it. Now, in the coin analogy, we only updated our count if a specific phenomenon was seen. And in that case, we updated our count when we saw heads. In the example of HYPERLOGLOG, every time we see a user, we only update a bucket value if some other specific phenomenon is seen. And the phenomenon that we actually care about is based on how bits are distributed when we hash a username. So more specifically, what we're looking for is the position of the first 1 bit that occurs after we hash a username. And we only update our bucket value if this position is greater than an existing value. So I'm going to go through a very simple example. Let's say we have a set of buckets, and all these buckets, all the values in these buckets are initialized initially to -infinity. We ingest some data, and we see a unique username. We hash this username, and we get a series of bits. And we look at the position. Whoa, it's hard to point this. We look at the position of this one, and the position here is 2, so we update our bucket value because 2 is greater than -infinity. Similarly, as we ingest more and more users, we look at the position of the 1 bits for each of these users, and we update our bucket values accordingly. Now, at some point later, basically, we see another user that ends up hashing to the same bucket, and in this case, the position of the 1 is 3, which is greater than our existing value, so we update our bucket value. Now, what's actually being stored in these buckets is a probability distribution. And the authors of the original papers basically bust out some magic. And by magic, I mean math. So they use math to convert the values in the buckets to an actual cardinality estimate. And it's incredibly cool. Okay, so in terms of how we store our data, we don't store every single unique username that we've seen. We don't store this set of strings. What we store is just the buckets themselves. And these buckets are like absolutely tiny. And like, you know, it's a kilobyte basically to represent some of these buckets. The accuracy of the results actually varies on the number of buckets you choose to use to store your data. So the more buckets you use, the more accurate your result is going to be. And it goes, once again, back to this idea that if you want your results to be more accurate, sometimes you just have to use more storage. Oops. And as a final note here, basically the buckets that we have are completely mergeable, so it's very easy to summarize our data with these buckets. So we can have like hourly views of our data, or we can have daily views of our data. Okay, so I'm now going to hand things off to my colleague Nelson here, who's going to talk a little bit more about the results that we've seen using HYPERLOGLOG, and the second of our two case studies, which talks about how to build approximate histograms and approximate quantiles.
You were doing such a good job. You can just go ahead and finish off the talk. Thank you, Fangjin. So again, we look at these two plots, which are rapidly becoming familiar. On the left, we see storage, and on the right, we see computation time. So in Salmon, we see that as you add more values, more users to the hash set, that as the cardinality increases and you add more and more unique users, the size in bytes increases linearly and without bound. By contrast, look at the approximate representation, the HYPERLOGLOG object. And for the size that we use, it's around 1 kilobyte. So there's a cap on the size of this object at 1 kilobyte. And if we look at the computation, then it's pretty easy to understand that if you're combining 100 objects, each 1 kilobyte in size, then you can do that in constant time. And the time does not grow despite the increase in cardinality of the underlying objects. By contrast, we see that the hash set time, in order to combine all of these hash sets together, increases linearly in a way that matches the size of the underlying object. But this isn't without any downsides. And as Fangjin mentioned, the error is approximately 3%. So what does that mean? Well, we ran one simulation where we generated several users, and we see that our estimates ranged in error from 0.5% to 2%. So the 2% occurred at a cardinality of 75. So when there were 75 users, maybe we said there were 76.5, which is close enough for our clients. And again, there's the standard size accuracy trade-off. So if you demand higher accuracy, you can choose to allocate more bytes to this object. So for case study 2, we're interested in determining the distribution of values. Why? Well, quantiles come up in many cases. For instance, service level agreements often mean that you put your guarantees, for instance, in terms of performance, in quantiles like 95th percentile or 99th percentile performance. And histogram plots are also a nice way of visualizing the distribution of certain values. In our situation, we're dealing with hourly truncation, but this is very general, and you can use the same principles for minutely or daily truncation. So this is the bid price event stream that Fangjin introduced. But instead of computing sums and averages, our problem here is to compute quantiles and to plot histograms. The one exact solution is to store the bid prices, the individual bid prices, into this array over here. So in the second hour of the day, we saw these 3 prices, and we store them as entries in this array. So that's how we go from the raw prices into these summarized hourly prices in an array. And how do we merge these hourly arrays together to come up with a daily array? Well, you can just concatenate them. And finally, from the concatenated array, you can compute quantiles and plot a histogram. And in this example, it's pretty easy to do that. But when you're dealing with billions of events, it could be challenging. So the characteristics of this exact solution are linear storage and linear time storage and computation, and it's 100% accurate. But there's a pretty obvious problem. Let's say you decide to take the advice of the earlier section of the talk, and you decide that you want to pre-summarize your data, and you also want to compute the distribution of values for some column, and you do it the exact way because we haven't covered the approximate way yet. Then the storage for that column can quickly dwarf the rest of the row as your array grows without bound. So we're going to try to find a data structure that has a limit on the size of the object. In this case, it'll be bounded by a constant. This is what we did in the cardinality estimation case. We used HYPERLOGLOG to achieve that. So the exact approach that we're using, we call it approximate histograms, and it comes from a paper these two researchers, Ben Heim and Tom Tov, I believe it was ICML 2010. They introduced these approximate histograms in order to build decision trees in a streaming fashion. And depending on how you count, it's sublinear to linear storage and computation complexity. And accuracy is somewhat complicated because we're going to get out of these objects both quantiles and histogram plots. And there can be various kinds of parameters. We'll return to this, but in short, we saw that the accuracy was pretty good for most of our cases. So here's an example where we're dealing with 40 bid prices ranging from $3.50 to $17. And this is what they look like if you plot them out. So how would you summarize these 40 numbers? One way, if you care about squared error loss, is you can use the sample mean. And in that case, you actually can't do any better than the sample mean. So let's take a look at that. It's $9.80. And if you also add a count, and you represent this by, on the x-axis, here's the sample mean, and the y-axis is the count of the values, so the 40 prices. Then from these two numbers, you can calculate the total revenue. But this is a pretty poor summarization, so let's add more sample means. This also isn't so good, so let's try more. Now we're getting somewhere. So the way to read this again is there's one value with a sample mean of 3.5, and because there's only one value, that's exactly the value. Here, these four have a sample mean of 5.8, and so on. So we know how to convert from raw prices into this summarization. And because we're only storing 10 pairs here, that's 20 numbers, and that's less storage than the 40 raw prices. And one other thing to observe is that there's no price that is far enough away from its closest sample mean. So it seems like the accuracy, whatever that means, of this approximation is pretty good. Now we're going to look at how we merge two histogram objects together. So let's say we have these 40 prices in blue and the corresponding histogram object here. We're only using 8 pairs in this case. And we add 40 more prices in red, and we construct the corresponding histogram object. What the authors of the paper suggested was to iteratively merge the closest two bars together. And you update the counts just by taking the sum of the counts. And you can update the sample mean with the weighted mean. And you get this combined histogram. So we can see it left these two bars alone because they were off to the side, but it merged this 5 and the 7 to get a 12 here. And typically we combine many histograms together, and then finally we need to get useful information out of all these combined histograms. And one procedure that we're going to look at is how to answer the question, given this approximate representation, how many values are there less than or equal to some value x? Why is this important? Well, if you want to plot a histogram, basically you just need to repeatedly count inside of buckets that are defined by two endpoints, an x and a y. So you can ask, how many values are less than or equal to y? And subtract from that the number of values less than or equal to x. And that gives you an estimate of the count in that bucket. And you do this repeatedly. So here we have 18 prices. And we're trying to approximate them with an approximate histogram with 3 pairs. And we'll start with a simple example. Let's ask how many values are there in this histogram. Remember that we don't know the prices, they're just there for illustration. How many values are less than or equal to 5.5? So we know that there are 10 values around that sample mean, and we have to make an assumption. And the authors of the paper suggest a pretty reasonable assumption that half the values lie to the left and half are to the right. So we say there are 5 values less than or equal to 5.5, and that's exactly right in this case. So let's try a harder example where the value x doesn't align perfectly with some sample mean. Let's try what's the number of values less than or equal to 10. This lies between the 2 sample means, 5.5 and 12.8. And from our assumption earlier, the contribution to this region from this bar is half of 10, which is 5. And the contribution to this region from this bar is half of 4, which is 2, and they add up to 7. So now we have to apportion these 7 points. And the authors suggested looking at the ratio of the area of this trapezoid to the bigger trapezoid. Why? Because the idea is if there's a taller bar, there are more values around there. And it's one way of taking that information into account. And if you do this, then you get 5.05 in this region for a total of 10.05 less than or equal to 10. And if you count things up, the actual answer is 10. So it's pretty accurate in this case. These are the storage and computation plots again. And it looks a little bit weird for the float array list case. We decided to go with float array lists for the exact solution because they're a little bit smarter in terms of how they grow the array list. So it doesn't do it too often, it does it exponentially. And we get this step function that if you squint, it does look like a line and it increases without bound. And there's a cap here on the approximate histogram size, and for us it's around 600 bytes. But again, there's that parameter that controls the trade-off between the accuracy and the storage. And we're pretty happy with this value, but if you demand higher accuracy, then you can make it bigger. And the computation time is a similar story, where in under a millisecond, you can combine all of these approximate histogram objects together. And this is irrespective of the number of values inside of the histogram, because there's a cap on the size. Compared with this sort of noisy linear function. So now let's take a look at the accuracy. And here we're plotting the estimated counts in various histograms against the actual counts. And up top, this is with only 5 pairs, so it's not going to be a very good representation. And the way to read this is down here, estimated. So we estimate maybe 100,000 values in the 0 cent to 5 cent bin. And the actual answer is just over 6 million, so terrible. But if we look at 50 and 200, then the 2 histograms side by side are almost indistinguishable. And that's what I mean by the accuracy is pretty good. You could do the same thing for quantiles. So let's take a look at we saw a bunch of micro benchmarks, but let's see what happens in an actual production cluster. So we spun up 100 machines on Amazon, and these were pretty big machines. They totaled 1,600 cores with 6 terabytes of RAM. And if you do the summarization process, then this cluster can actually churn through those rows at a rate of 27 billion per second, just counting them. But if you want to add up your hourly and daily prices, then it's a little bit slower, 16 billion rows per second, which, given our averages, our average compression ratios, corresponds to 640 billion raw rows per second. So let's just think about what this means. If you're a small business and you sell 500 billion items a day, and you want to be able to do analytics on your prices and slice and dice and look at time series over various subsets of your customers, then the maximum time you'll have to wait for any of these queries is 1 second if you give it enough machines. If you're looking at cardinality estimation, then it's a little bit slower because you have to iterate through the objects and then update the maxes. But it can still do this processing at a rate of about 4 billion rows per second. And combining histograms is even slower. It's only 1.5 billion objects per second. But keep in mind that each object can itself represent tens to hundreds of values, prices, for instance. So if your data are amenable to summarization, and if you're interested in just computing numbers and sums and averages, then well, your mileage may definitely vary depending on the exact distribution of the data. But we saw, for instance, a 40x fold improvement in terms of speed and also storage. And it's 100% accurate if you don't really care about the exact millisecond, as Fangjin mentioned. Now, for harder problems such as cardinality estimation or approximating the distribution, if you're clever about it, then you can achieve a similar speed up, 1 or 2 orders of magnitude. And the downside here is it's not quite 100% accurate, roughly 97% accurate. And this is, I guess, kind of obvious, but a 40-fold difference in cost. It was the difference for us between a successful business model and a business model that is most definitely not successful. So this is how we enable what we call interactive queries that are accurate enough.